you are probably listening to this with headphones on right now, or maybe through your car speakers.
Yeah, that's highly likely.
And as you sit there, you might feel like you're just passively absorbing information. But physically, your nervous system is actually reacting to the rhythm of my voice.
Right, to the subtle air pressure changes in the room.
Exactly. The acoustic waves hitting your eardrums right now, the sounds surrounding you, is quietly altering your biology as we speak. Which, it makes you wonder, what do operatic mice, fetal concerts, and crocodiles breathing helium all have in common?
It sounds like the inventory list for the world's most chaotic, heavily funded pet store.
It really does.
But these are all real subjects of genuine scientific inquiry, and they all point back to that exact phenomenon you just mentioned.
So today's deep dive is exploring a really fascinating column about the Ig Nobel Prize and its deeply surprising connections to sound and music.
Yeah, that's a great topic.
Our mission today is to explore that intersection where the hard science of measuring the world kind of meets the artistic expression of feeling the world.
Right, and to really grasp that intersection, we have to look at the philosophy behind the Ig Nobel Prize itself. It was founded back in 1991 by the Annals of Improbable Research.
Think of it as the quirky younger sibling to the regular Nobel Prize.
Exactly. Their entire guiding motto is to honor research that first makes people laugh and then makes them think.
It's this space where reason and play intersect, because we usually treat music as a purely emotional experience, right?
Yeah, like a wave of sound that just washes over us.
Right. It gives us a sense of nostalgia or hypes us up for a workout. But the research highlighted in our sources proves that sound is a literal physiological trigger. It wields this undeniable physical authority over the living body.
It really does, and the 2013 Ig Nobel Medicine Prize is the perfect demonstration of this.
Oh, the mice study.
Yeah, the prize went to a researcher named Masanori Nimi from Teikyo University. And it was for this experiment involving mice that had just undergone heart transplants.
Which, just to set the stage, a heart transplant is a massive, highly delicate medical trauma.
Absolutely.
The body's immediate biological response is to mount an immune attack against the foreign organ, which is why transplant rejection is so incredibly common.
Right, so the research team took these recovering mice and divided them into 3 distinct groups. They wanted to test how environmental sound affected their physical recovery and their stress tolerance.
Okay, so what were the 3 groups?
Well, Group 1 listened to opera, specifically Verdi's La Traviata. Group 2 listened to modern pop music, and they used Denya as the baseline for that.
Okay, yeah.
Yeah. And Group 3, the control group, they simply sat in complete silence.
So when you look at the survival rates after such a major medical event, the silent group and the pop music group averaged a survival time of about 7 days.
Right, just a week.
But the opera group, the mice, listening to Verdi, saw their average survival rate extend all the way to 27 days.
Which is just wild.
It's incredible. Going from 7 days to 27 days is not a slight margin of error.
Yeah.
That is a massive physiological shift. But we need to unpack the mechanics of this a bit.
Yeah, let's do it.
Because, is it just the fact that it's culturally revered music?
Mm.
Or is there a structural reason why classical music specifically impacted the mice's immune systems? Because it feels almost like Verdi wasn't just a playlist choice here. It was like a prescribed medical dosage of rhythm.
A prescribed medical dosage of rhythm. I like that it captures the mechanism beautifully because, the mice obviously don't have a refined cultural appreciation for 19th century Italian opera.
Right, they are music critics.
Exactly. What's actually happening is that the classical structure and the complex mathematical rhythm of the composition act as a biological stimulus.
Okay, how so?
Well, when a mammalian body undergoes severe trauma, the sympathetic nervous system kicks into overdrive. It floods the body with stress hormones like cortisol.
Which is really bad for recovery, right?
Very bad. It severely impairs the immune system's ability to regulate itself and accept the new organ.
So the music is essentially acting as an acoustic beta blocker.
Precisely. The highly ordered structural rules of classical composition, the specific tempos, the predictable harmonic resolutions, they interact with the autonomic nervous system.
Oh, wow.
Yeah, it helps synchronize the heart rate and actually triggers the parasympathetic nervous system, which is the rest and digest mode.
So it's actively calming them down on a cellular level.
Right. It actively lowers the stress hormones, which reduces the inflammatory response that leads to organ rejection. So this experiment really blurs the line between a purely artistic experience and a measurable mechanical medical treatment.
That's just fascinating. And, if sound has that much physical authority over a recovering adult organ, it really makes you wonder what it does to a body that is just starting to form.
Oh, absolutely.
And our sources point directly to another Ig Nobel winner that takes this into human physiology. So in 2017, the Medicine Prize went to the Institut Marquès in Barcelona for developing something they called the baby pod.
The baby pod, yeah. This is a specialized vaginal speaker designed to test how fetuses react to music while still inside the womb.
Now, people have been playing music for fetuses for decades, right? Usually just by pressing a pair of headphones against the mother's abdomen.
They have, but the researchers found that playing sound externally through the abdomen produces a pretty minimal reaction.
Which physically, that makes a lot of sense. The sound waves have to travel through layers of skin and muscle tissue, and then all that amniotic fluid.
Right, and water is incredibly dense. So the amniotic fluid acts as this massive acoustic dampener. It basically filters out all the high frequencies and leaves the fetus with just a muffled, distorted bass rumble.
So they aren't hearing Mozart, they're hearing a club from down the street.
Exactly. So the baby pod completely bypassed that acoustic barrier. By providing direct vibration and clear sound internally, the fetuses responded significantly.
What kind of response are we talking about? Like a heartbeat change?
More than that, they weren't just showing a slight shift in resting heart rate, they were actively moving their mouths and their tongues far more than when the sound was played externally.
Wait, so they are essentially trying to vocalize?
It seems that way.
Yeah. That's amazing. It highlights the absolute earliest developmental stages of auditory reaction. I mean, long before a baby takes its first breath, the physical brain is wiring itself, building those neural pathways for communication and feeding in direct physical response to the frequency of sound waves.
Yeah, both the operatic mice and the baby pod fetuses show us that living bodies are fundamentally built as acoustic receivers. The external structure of sound dictates an internal biological reality.
Okay, so if the body physically reacts to the structural rules of sound, what happens when biological creatures rely on those inescapable physical laws of sound to exist in the wild?
Well, for that, we step out of the medical laboratory and head straight into the swamp.
Nice transition.
Thank you. So, the 2020 Acoustics Prize was awarded to Takeshi Nishimura at the Kyoto University Primate Research Institute. And this was for analyzing the vocalizations of a crocodile.
And this is where it gets weird, because to do this, the research team placed a crocodile into a controlled environment filled with a helium-oxygen mixture, which is known as heliox.
Right, they basically gave a crocodile a giant party balloon.
Right, and they did this because they wanted to analyze the formants of the crocodile's roar. But before we get to the helium, we should probably clarify what a formant actually is.
Good call. So think of a biological vocal system like a trumpet. The vocal cords are the mouthpiece, creating the raw vibration, or the pitch.
Oh.
The vocal tract, so the throat, the mouth, the snout, that's the brass tubing of the trumpet. Formants are the specific frequencies that get amplified as that raw sound travels through the physical shape of the tubing.
So the tubing itself dictates the final sound.
Exactly.
Now, bringing the helium back in. Because helium is much less dense than normal air, sound travels through it much faster, right?
Right.
So when the crocodile inhales the helium, it doesn't change the vibration of its vocal cords. The mouthpiece stays the same. But the faster-moving air alters how the sound resonates within the vocal tract.
Right. The formants actually shift upward. And by tracking how those formants changed in the helium chamber, the researchers confirmed that the resonance structure of the crocodile's roar is intrinsically linked to the physical size of its vocal tract.
Okay, I get the physics of the helium altering the resonance. But practically speaking, couldn't a scientist just use an ultrasound to measure the crocodile's throat? Why go to the immense trouble of building a helium chamber for a massive reptile?
It sounds absurd, but exactly what the helium experiment achieves is proving that vocal resonance is an honest acoustic signal.
An honest acoustic signal. What does that mean in this context?
Well, in the wild, animals use vocalizations to establish dominance or attract mates without having to actually engage in physical combat. If a smaller crocodile could somehow manipulate its throat to mimic the deep roar of a larger crocodile, the whole communication system would fall apart.
Oh, I see.
Yeah, so by changing the density of the air and measuring the resulting shift, Nishimura proved that biological communication is strictly governed by physical and acoustic principles.
So a crocodile literally cannot fake how big it is.
No, it can't, because the physics of sound simply will not allow the formants to lie.
They are quite literally bound by the laws of physics every time they open their mouths. That's incredible. And, that concept of an honest acoustic signal, connects perfectly to another study in our sources.
The frog study.
Yes. The 2005 Biology Prize was awarded to a team for identifying frogs purely by their voices.
Right, because if the physics of sound are absolute, then the resulting vocalization is essentially a biological fingerprint.
So you don't even need to see the animal.
Exactly. The researchers demonstrated that you don't need to physically capture or even see the frog if you understand the acoustic laws governing its vocal tract. You can identify the species, the relative size, and even the specific individual just by decoding the sound waves echoing through the environment.
It's like nature has a built-in sonar system based entirely on acoustic truth.
It really is.
So we've looked at how animals are bound by the physics of sound and how scientists use sound to test biological limits. But the source material takes this a step further, examining how humans, specifically scientists and musicians, actually mirror each other's experimental methods.
Yeah, both disciplines are ultimately trying to map the laws of listening to understand the human experience.
And the Ig Nobel ceremony itself actually embodies this overlap between scientific rigidity and musical structure. The organizers use rhythmic constraints to manage the presentation of complex data.
They do. They have entire presentations of complex scientific papers delivered in an opera format.
Which is just amazing to picture.
Right. And they also enforce this strict rhythmic constraint for acceptance speeches. So scientists are given a 24-second window to explain their research, and that is immediately followed by a 7-word summary.
So they are essentially applying a musical time signature to scientific communication.
Yes, exactly. But the crossover works in the other direction, too, with science turning everyday listeners into data points. And a great example of this is the 2019 Peace Prize, which went to a team from the Netherlands and Poland for their study on misophonia.
Misophonia. That's the intense, often overwhelming anger response people have to incredibly specific, unpleasant sounds, right?
Yeah, exactly.
Like sound of someone chewing loudly or nails on a chalkboard or even just heavy breathing.
Right. And the mechanism behind misophonia is a perfect example of sound bypassing our logical brain entirely. Modern neuroscience utilizes fMRI scans, which measure blood oxygenation levels in the brain to track exactly what happens during these auditory events.
So what do they find?
Well, when a person with misophonia hears a trigger sound, like loud chewing, the acoustic signal completely bypasses the higher cortex. It hyperactivates the anterior insular cortex and the amygdala, which are the emotional and fear processing centers of the brain.
So the brain is literally interpreting the frequency of someone chewing a potato chip as an evolutionary threat.
Yes. It's acting like a false alarm for a predator or a severe distress signal.
That is wild. The scientists are taking the highly subjective emotional experience of hearing something annoying and using medical imaging to turn the listener into a measurable psychological and neurological data point.
Exactly. And while the scientists are borrowing the tools of subjective listening to map our emotions, the musicians are borrowing the rigidity of the scientific method to create art.
Right. The column highlights several artists who utilize these rigid frameworks, most notably John Cage and his famous 1952 piece, 4 foot 33.
Oh, yeah. Such a controversial piece.
For those unfamiliar, 443 is the piece where a performer sits at a piano, closes the lid, and does not play a single note for exactly 4 minutes and 33 seconds.
Right. It forces the audience in the concert hall to listen to the ambient noise of the room.
Yeah, the coughing, the shuffling in seats, the hum of the ventilation system.
And it is usually framed as a piece of avant-garde philosophical art about the nature of silence.
It is, but if we view it through the lens of our deep dive today.
Right.
Oh, wait, you know what? John Cage's 433 is functionally identical to the silent control group from the mouse heart transplant study.
Oh, wow. Yeah, you're right.
Right. The researcher in the lab and the musician in the concert hall are running the exact same structural test. They're both asking, what happens to the biological and emotional state of our subjects when we introduce a literal void of engineered sound into their environment?
That's a brilliant connection. The underlying purity of questioning is absolutely identical. Musicians observing the world through sound are essentially acting as acoustic scientists. And another example from our source material is Brian Eno, who pioneered generative music back in 1996.
Generative music. That strips away the traditional idea of a composer meticulously writing down every single note, right?
Exactly. Eno brought algorithms, chants, and rigid structural rules into his art. He wasn't composing a static song. He was building a mathematical system, setting the initial variables, and just letting the sonic experiment run its course to see what emerged.
It's the musical equivalent of running a scientific simulation.
It really is.
Yeah.
And we see this methodology evolving even further with modern artists who use raw data as their instrument. The column notes the Icelandic band Sigur Rós, who have performed live concerts that convert human brainwaves directly into synthesized sound.
That's incredible.
Yeah, or the composer Ryuichi Sakamoto, who took raw climate and environmental data and translated it into acoustic compositions.
So they aren't just making interesting noises. They're taking the measurable, quantifiable data of the physical world and translating it into the emotional language of music.
Exactly.
Whether it's Brian Eno's algorithm generating an ambient melody or an fMRI machine measuring a listener's amygdala spiking in response to a chewing sound, both the artist and the scientist are trying to map the exact same thing, human perception.
And this brings us to a really beautiful synthesis of everything we've explored today. Beneath the laugh-out-loud quirkiness of vaginal speakers for fetuses and crocodiles breathing helium balloons, there is this profound shared reality.
Which is?
Science and art are not opposing forces. They are two distinct methodologies for making sense of the universe. Science uses measurement to find objective truth, while art uses aesthetic structure to find emotional truth.
But the boundaries between the two are incredibly porous. I mean, the mathematical structure of classical music can physically lower the cortisol levels in a traumatized mouse.
Mhm.
And the physical density of the atmosphere completely governs the social communication of a massive reptile.
Right.
When these disciplines meet, they reveal that sound is never just sound. It is a physical force, it's a biological signal, and it's an emotional trigger, all wrapped into one invisible atmospheric wave.
Yeah, the motto of the Ig Nobel Prize, first it makes you laugh, then it makes you think, is profoundly effective here. Because the image of a mouse listening to vary in a tiny hospital ward is inherently funny.
It really is.
But the implications force you to think about the deep vulnerability of our own biology to the acoustic environment surrounding us.
Which leads to a final thought for you to carry into the rest of your day. If avant-garde musicians are essentially acting like scientists, mapping our emotional responses, and medical researchers are proving that specific rhythms can literally extend the life of a transplanted organ, what everyday sounds in your own environment might secretly be altering your biology right this very second?
Oh, that's a great question.
Think about the low-frequency hum of your refrigerator, or the rhythmic cadence of the traffic outside your window, or the sudden, sharp pitch of your phone's notification chime. If your nervous system is constantly reacting to acoustic pressure, what invisible experiments are you the subject of right now without even realizing it?
It is a fascinating and slightly unsettling lens through which to view your daily life.
It really is. Well, that brings us to the end of today's Deep Dives. Thank you for joining the conversation, and as always, keep questioning the world and the invisible waves around you.